Hello, this is Photios Logothetis and I will be explaining our neural point light approach for the multi-view photometric stereo problem. This is a joint work with Ignas Budvitis and Roberto Cipolla. The photometric stereo method aims to reconstruct the surface of an object from multiple images taken from the same point of view with varied illumination. The multi-view case adds multiple camera viewpoints for all illumination images, which allows for a much better reconstruction quality. Our method models point light near field illumination, and it's applicable to highly spectral objects such as the Buddha statue, whose images contain cast shadows and self-reflections. As a brief overview, our methods consist of three key steps. Firstly, single view photometric stereo is performed on the views to obtain normal maps. Secondly, a neural sign distance field is initialized to fit these normal images with normal and silhouette loss. Finally, the neural SDF is refined through full near-field point light volumetric rendering by applying losses to the render intensity images as well as the surface normal and object silhouettes. In this slide, we explore related work. Neural surfaces have recently revolutionized multi-view reconstruction methods. However, the adoption of neural intensity rendering has been slower for the photometric stereo community. Indeed, the best competing multi-view photometric stereo approaches are Supernormal and RBN-NEUS, which both aim to render single-view normal and albedo maps using supervision from single-view estimation networks. Thus, this single-view normal reliance makes them perform suboptimally in sparse light settings where normal estimation networks become unreliable. The most similar approach to ours is by Brahimi et al., which employs physics-based point rendering using the simplified Bisney BRDF. This, however, makes it vulnerable to global illumination effects such as cast shadows and self-reflections. Our method combines the best of both worlds to maximize performance and gain robustness to sparse light setting. Additionally, we employ a fully learned material model and explicitly ray-trace cast shadows, and thus significantly improve the state of the art on the sparse light setting. I will now be elaborating further into the details of our method. We parameterize the surface through a sign distance field, which in turn is encoded using the Siren neural network, which provides continuous differentiable analytic normals and allows for fast convergence. The Siren network also includes a scalar albedo, which is used for grayscale rendering. We know that we avoid to render RGB images in order to minimize synthetic to real gap. We follow the standard of the volume rendering literature and sample points around the rays to render and accumulate intensity through opacity. In addition, ray tracing from surface intersection points to light sources is performed in order to compute cast shadows, which are essential for accurate intensity rendering. To further elaborate on the intensity rendering, we assume that the image irradiance equation consists of the product of the following terms. Firstly, there is a point light attenuation factor A, which accounts for light propagation from a non-uniform point light source M, with direction Sm and attenuation factor μm. This is standard term in the near field photometric stereo literature. Secondly, we account for variable point albedos ρ sampled for the Siren network, as well as soft shadow indicator variable S's, which are computed with the volumetric ray tracing described earlier. Finally, we assume that the surface has a general but uniform material BRDF, which is generally a function of the relative angles between normal lighting and viewing vectors. We represent this BRDF function with a small 3-layer MLP, which is jointly optimized with the surface. We evaluate our method on the Diligent multi-view dataset, which is the standard benchmark of the field. Diligent contains 5 objects, and each one of them has 20 views with 96 photometric stereo images. To demonstrate the practicality of our method in a more challenging setting, we also include several spastic cases up to 6 views with 6 lights only. For all experiments, in order to get a fair evaluation metric, we crop the ground truth and reconstructed meshes by removing the bottom 6 mm, which are occluded. We then compute bidirectional Hausdorff distance using MeshLab. Here we present a quantitative results on the full Diligent benchmark. We observe that our method matches the best competing approach of Supernormal at an average error of 0.2 mm. It is interesting to note that the next best competitors are only marginally worse at 0.22 and 0.24 mm respectively. Indeed, a qualitative representation of the error maps also confirms that all the best competing approaches are roughly equivalent, with roughly similar error distributions on each object. Thus, to amplify this difference between methods, we consider several sparse light and view settings. Indeed, on the most challenging 6 views with 6 light case, we significantly outperform the second best competitor, Supernormal, with 0.38 versus 0.61 mm average errors. Our paper also contains several other sparsity experiments which are visualized here. Indeed, on these settings our method shines and achieves comfortably state-of-the-art performance. Finally, to mitigate the saturation of state-of-the-art on diligent dataset, we have a new dataset in preparation. This new dataset, Lucas Multiview, contains 15 objects captured on a near field setting of up to 40 cm from the camera. This data is already available online. To sum up, in this work we present the first fully neural field point light rendering multi-view photometric stereo method. We explicitly use single view normal and 3D surface rendering losses and significantly improve the state-of-the-art on sparse light setting. Further work on the multi-view photometric stereo field includes differentiable ray tracing for transparent material rendering, temporal modeling for dynamic shape reconstruction, as well as neural rendering processing caching for efficient rendering.